loading the filter. Yeah, let's recap a little bit. Yeah, do a simple revision. And this one, yeah. Okay, last week we have discussed up to this point. We have to discuss on the sizing of the nitrification tank. Yeah, sizing of the nitrification tank. If you still remember, yeah, I hope you still, yeah, because we have for the moving bed bioreactor, we have two systems that we have to design. The first one is going to be the main tank, yeah, which is the BOD removal tank, and the second one is the nitrification. There are two systems, yeah, in the MBBR process. The one that we watched in the video, previously in the video on moving bed bioreactor system, the system was designed only to cater for the BOD removal. Yeah, but this one the system has been designed to remove both nitrogen as well as BOD. For that reason, we need two separate tanks. Okay, you know why that we cannot combine them in one same tank? Because the oxygen that required for the removal of each of the processes is significantly different. Yeah, is different. Therefore, it has to be designed separately. Okay, so we have discussed last week to do the sizing about the carrier surface area, how to come up with the volume, as well as to come up with the sizing of the tank. We have also discussed on how to design for both BOD removal tank as well as nitrification tank. Yeah, and also we have discussed on how to design the sedimentation tank. Sedimentation tank in this case is a secondary clarifier. Yeah, secondary clarifier. Okay, SALR is a surface aeration loading rate. Yeah, secondary clarifier is this one. Yeah, so in my notes I put both a secondary clarifier as well as sedimentation tank. Yeah, so because this is a biological process. Yeah, definitely it will produce large volume of inert cell. Yeah, inert cell. So that we have to consider of having the secondary clarifier to allow the settlement of the sludge. Yeah? Okay. All right. So now, yeah, after we have come up with the design, with the sizing, with the volume of the filter required, based on the loading of BOD as well as nitrogen to be removed, yeah, so that we are in the second section, yeah, of moving bed bioreactor design, which is to calculate the aeration requirement. Yeah, to calculate calculation of aeration requirement. Okay, so why? Why aeration is required? Yeah? Why we need to supply the oxygen, yeah, pure oxygen into the system? Because it's required during the mixing of the biofilm media to maintain the dissolved oxygen level, yeah, for the survival of aerobic bacteria. Okay, what is biofilm? Yeah? Biofilm is the layer which is developed within the surface of the filter. Yeah, if you still remember in my previous slide, yeah, I did share with you a photos, yeah, where how does the biofilm which has been developed after 3 months of exposure of the filter in certain wastewater tank, yeah, so that biofilm is required to develop because this slime layer is the layer where microbes can attach with, yeah. So this is why that aeration is required. Yeah? For BOD removal and for nitrification process, yeah, to maintain the aesthetic condition, yeah, and to avoid foul smell. Okay, if you notice, yeah, the words that they use here, BOD removal and nitrification process, yeah, because nitrification process is not the removal. Why don't we have nitrification removal? Because it's not a nitrification removal. The one that we would like to remove during nitrification is nitrogen. Yeah, so nitrification process is the process required for nitrogen removal. Yeah, so that is the correct word, the correct sentences to be used, so that it can reflect your understanding. Okay, first we have the terms of for BOD removal. BOD removal is correct, and for nitrogen nitrification process. So nitrification process is required for nitrogen removal. It's a continuation process from nitrification followed by denitrification process. Then only nitrogen can be removed. For moving back bioreactor, depends on the concentration or the constituent, or the ingredient of the wastewater or the waste to be treated. Not all the time that we have to acute with the nitrification process tank. Yeah, because in some cases, if nitrogen is not high, so there is no need to provide an extra tank for the removal of nitrogen. For that reason, BOD removal tank is sufficient, to be acute for the MBBR system, moving back bioreactor system, and having aeration process can also avoid the foul smell. Okay, at the bottom of this figure, I have classified how do we how do we classify the size of the diffuser. If we are going to employ a fine pores diffuser, then the size should be from 0 to 3 mm. Yeah? So next is also fine diffuser is a moderate fine diffuser 3 to 5 mm. Then coarse diffuser, which is 5 to 50 mm. Yeah? And another one is hole in pipes. This is over 50 mm. So these are the ranges of the holes in the diffuser that they use in wastewater treatment process. So diffuser ni is just like the shower head. Yeah. So if we can imagine, so that how do we supply oxygen into the bottom part, which is located. This normally located at the bottom part of the tank, so that oxygen can be supplied. Most of the time, they will be using fine pores diffuser or moderate pores diffuser. You know why? Because the smaller the bubble size, because once we supply the oxygen, it will produce bubbles. The smaller the bubble size, the better will be the surface area contact between the wastewater as well as the oxygen. So that in order to increase the oxygen transfer rate, we have to use a fine pore diffuser. We have to always maintain a smaller bubble size. Because the smaller the bubble size, the better the surface area. The better the surface area will be the better the oxygen transfer. So that is the concept. The reason why that we have to use the smaller bubble size, because we would like to increase the surface area or the contact between wastewater as well as the oxygen. Okay, these are the example of tubular diffuser in moving back bioreactor. This is how the oxygen that being supplied. Okay, what will be the air flow rate or inlet of diffuser? Okay, this is what we would like to calculate today. We have come up with a design last week. We have identified the volume of the filter required, and now we would like to calculate how much the airflow rate required. So this is very important to ensure the quality of the effluent. Is depend on the BOD and nitrification. For BOD, 1.2 kg of oxygen required for every kg of BOD applied. Okay, depends on the BOD load that we would like to treat. So how many kg? Let's say you have 10 kg. So you need at least 12 kg of oxygen. That's how. Because every kg of BOD is required 1.2. But for nitrification, for nitrogen, for every kg of ammonium ions, it will need about 4.6 kg of oxygen to oxidize to nitrate. Because from nitrate to from nitrate to nitrates. So this is it doesn't exist in the form of nitrogen, but it will exist in the form of ammonium. This is our first equation in the part A of nitrification process. So ammonium, for every each of kg of the ammonium, each kg of ammonium is equal to about 4.6. That's why I said just now, in order to oxidize the ammonium, is required 4 times of the BOD. It's equal 4 times oxygen as compared to BOD. Okay, these are the value that we are going to use to calculate for the uh, amount of oxygen required. Okay, now I would like you to focus to this calculation because I want you to calculate later. This example is going to be on how to calculate the oxygen required um, uh, for BOD removal. Okay, later I want you to calculate oxygen required for nitrification process. Okay, let's see one by one. Okay, oxygen required for the BOD, 1.2 kg of oxygen is required for every kg of BOD applied. In our design, they are going to treat about 0.5 million liter day or mega liter day MBBR plant. MBBR plant. So the BOD is given, the 300 here is the BOD concentration, the 300 milligram per liter times 0.5 is the flow rate, so that you get about 150, 150 kg per day of the inlet BOD to be treated. Okay, thus if 1 kg require 1.2 kg of oxygen, now we have 150 kg kan? Okay, if 1 kg require 1.2, then you just times 150 times 1.2. So that, per day, the system require about 180 kg of oxygen per day, to treat about 150 kg of BOD, per day. Okay, which is equivalent to 0.5. This one you can pronounce, you can mention as million liter per day, or most of the time, in water or wastewater treatment, it will be mentioned as mega. It will be addressed, as mega liter per day. Okay, next, for air content, this is general, 23% of oxygen, which is 23 kg of oxygen per every 100 kg of air. Approximately about 77% of nitrogen, which is 77% of carbon dioxide per 100 kg of the air. Nitrogen per every kg of the air. So the density of the air is 1.2 kg per meter cube. Thus, the theoretical air required will be 180 kg per day divided by 0.23 oxygen times 1.2. So these are the volume, the volume of the oxygen required per day. Just now the answer is in kg, this one is the in volume, by volume, because the flow rate, when we measure the oxygen, when we use a compressor, and normally to supply the oxygen in a wastewater or water treatment plant, we need a compressor to supply, and it can only be expressed in the form of volume per day, not kg per day. But for to initiate the calculation, you have to start with kg per day, then only you can complete the calculation until you get in meter cube per day. Okay, exercise 1. Okay, I'm going to share this slide. This slide actually already uploaded into Trablast. I forgot to mention. But I'm going to share this slide in WhatsApp group so that you can see this slide. You can check slide number 54, slide number 53. Sorry. Slide number 54, slide number 55, and 56. So I want you to calculate oxygen requirement for nitrification process or nitrification tank. Okay. So now I have already the step. Yeah. Okay, for example, also requirement 4.6 kg of oxygen per kg of BOD applied. Apply ammonium nitrogen will be, you need to know the concentration, yeah, the concentration of the nitrogen times the total inlet flow. Total inlet flow is the same, yeah, so 1 kg of ammonium require 4.6 kg of oxygen. Okay, I'm going to share this in WhatsApp group so that you can proceed with the calculation. Yeah, I will give you 15 minutes to solve this exercise. Okay, let me share the information in our WhatsApp group. Yeah. Oh dear, Carbon have been um, requesting. Okay, so now I'm going to share the slide in our WhatsApp group. There will be one exercise that you have to solve now. I will give you 15 minutes to solve this exercise. In the previous example, we have discussed on how to calculate the oxygen requirement for BOD removal. Now you have to calculate for oxygen requirement for nitrification process. Yeah? Okay, let me share in our WhatsApp group first. Okay. Actually, you can also get this slide in Putra Plus, but it's okay. Huh? Um, because you need to solve it. You need to be quick, yeah, to solve this question. Okay, now I'm sharing into our WhatsApp group. Okay. Okay, the one that I'm sharing in our WhatsApp group. Let me share again. Yeah. Let me share again this slide. Okay, I'm now sharing in our WhatsApp group. First, the notes. Yeah, what will be first is the exercise. Now, I want you to calculate the oxygen requirement for nitrification tank. Okay, so given ammonium concentration is equal to 200 milligram per liter. Okay, you have the information here that for nitrification is required about 4.6 kg of oxygen. Okay, the one that I paste here is the steps to calculate the oxygen for the BOD. You can use exactly the same step to calculate for the nitrification, except you have to change the concentration because here we use BOD concentration of 300. So in your case, you need to use this concentration, and also you need to consider the weight of the oxygen requirement is no longer the same for the nitrification. Okay, so I will just stay online. Yeah, I will give you 15 minutes. I'll see you at 2:45. I will maybe call any of you, yeah, to share your steps and your calculation. So please write down the step because maybe you have to share the slide, the not really the slide. You have to share your calculation. Okay. So that's all. Thank you. Let me know if you have any question. Right, are you ready? Okay, can I have a volunteer to share with us the answer and also the step? Can you share your slide? Can you share not really the slide lah, right? Your handwritten calculation also can. Maybe Song you can try?
Can I just share the picture sent to our WhatsApp group?
Oh, in our WhatsApp group, okay. Oh, I haven't yet received. Already shared or what?
Just share.
Okay. Let me share this line. Yeah? Okay. So this is the solution from Song. Ammonia concentration is at 200 milligram per liter. So the inlet will be 200 times 0.5. The flow rate, yeah, 0.5 is the flow rate. Then since we know that for every 1 kg of ammonium to oxidize into nitrates is required about 4.6 kg of oxygen. Yeah, so 100 from here times 4.6, so 4 is required about 460 kg of oxygen. 77% yeah, of nitrogen content about 77%, so 70, which is equivalent to 77 kg yeah, of nitrogen gas. This is the density of the air. Thus the theoretical air required equal to 460 kg per day divided by 0.77 times 1.20. This is the density of the air. This is the concentration or the percentage of the nitrogen in the air. So more or less about 497, yeah. So here
Yes.
497.42
So,
meter cube per day. Okay, the step is correct, and I think the answer is also correct based on the step. Anyone have got different answer? Same. Dapat berapa? 497. Okay, 497.42. Okay, now very good. Thank you, Song. Yeah. Thank you everyone. Just now siapa? Nurin ni? Siapa yang cakap tadi? Sorry, saya tak tengok. Okay, thank you, Nurin. Alright, so now we are comparing. Just now, the answer that that Song calculated and everyone have calculated to get the oxygen required for the nitrification process is about 497. Let's take 500 lah, 500 meter cube per day. And the concentration of ammonium is only 200 milligram per liter. If we are to compare uh, with the oxygen required for the BOD, oxygen required for the BOD is that is about 651, about 650, even though the concentration is 300. So then now you have to bear in your mind, that whenever we are dealing with the nitrogen, the oxygen consumption will be 4 times higher. Sometimes the end of the calculation, towards the end of the calculation, you might be getting lower volume of the oxygen required. However, since you are dealing with domestic wastewater, sometimes the nitrogen is not too high. Let's say you are treating a livestock wastewater, then the nitrogen concentration you will get at least 1,500, 1,500 milligram per liter. In this case, since we are dealing with domestic wastewater, nitrogen is fairly low, around 200 milligram per liter. That's why the oxygen is lower as compared to the BOD. Okay. All right. Any question? We have done our section for the moving bed bioreactor. Okay. If there is no further question, we are going to move to another section of our lecture today. Before we move to next section of our lecture, today we are going to explore the joint methods for the removal of nitrogen as well as phosphorus. There are few methods which has been improved from the existing technology for a better removal both nitrogen as well as phosphorus. Okay, let's watch a few short video.
Anoxic means depletion or deficiency of oxygen. Biological treatment process by which nitrate nitrogen is converted to molecular nitrogen gas in the absence of oxygen is called anoxic process. This process is also known as denitrification. But microorganisms don't need oxygen in anaerobic process also. Then how anoxic process is different than anaerobic process? In anaerobic process, oxygen is toxic to microorganisms and they don't need oxygen for respiration and growth. But in anoxic process, biological treatment process will happen in absence of oxygen. But the microorganism will utilize oxygen from nitrate ions and these nitrate ions will convert in free nitrogen gas. Pseudomonas and Clostridium are the bacterial species which are responsible for reduction of nitrates back into largely inert nitrogen gas for completion of nitrogen cycle.
Okay,
Growth-based classification of anoxic process are divided into two categories.
Okay, before we move further, so this is a very good video to explain the difference between anoxic process and anaerobic process. What is the difference between these two processes? Anoxic process, both of these processes involve in the oxygen-free environment. However, in anaerobic zone, which is the lowest layer in any wastewater treatment or any pond, this is the layer without oxygen. In fact, oxygen is considered as the inhibition, considered as a toxic environment to anaerobic microorganism. Nevertheless, in anoxic zone, as I mentioned last week, the concentration of oxygen exists. This is less than 10%. Still, there are some oxygen, but very low, less than 10%. And the source of the oxygen is not from the environment itself, but the source of oxygen is from the nitrate, which is NO and O3. Let's continue.
Species which are responsible for reduction of nitrates back into largely inert nitrogen gas for completion of nitrogen. Responsible for bacterial species which are Clostridium are the bacterial species which are responsible for reduction of nitrates back into largely inert nitrogen gas for completion of nitrogen cycle. Growth-based classification of anoxic process are divided into two categories: suspended growth denitrification process and attached growth denitrification process. And arrangement-based anoxic process is also divided into two categories: pre-anoxic tank arrangement and post-anoxic tank arrangement. Thank you. If you like this video, please subscribe to my channel and like this video. Thank you.
Okay, if we are to compare between the
Anoxic arrangement.
Okay, if we are to compare between suspended growth denitrification process and attached growth denitrification process. Okay, let's recap a little bit. If we can revise, what is suspended growth? Suspended growth system is the system where we utilize a group of sludge in a tank. That is suspended growth system. While attached growth system is the system where we have a filter media. We provide the media for the microbes to stay within the tiny hole of the media. Okay, so if we are to compare the capability of nitrification and denitrification in these two systems between suspended growth as well as attached growth, the microbes which are capable to convert the ammonium into nitrates and nitrates into nitrogen gases, they are more they are happier they are happier in the environment with the attached growth process, because in this process there is one groups of microbes which is known as sulfate reducing bacteria. These types of microbes, they are the enemies for the microbes which promote the nitrification and denitrification. So sulfate reduction bacteria are more familiar in the system with the suspended growth process, suspended growth system. That's why nitrogen as well as nitrogen removal are better to achieve in the attached growth process, because sulfate reducing bacteria are not easily to growth in these types of system. Okay. All right, next video.
In wastewater treatment, denitrification describes the final step of the conversion from ammonium NH4+ to nitrogen gas N2. After ammonium is oxidized by microorganisms in a two-step process, ammonium is at first converted to nitrate NO3-. Nitrate NO3- is still in the wastewater, and although is less harmful than ammonia, it can still cause diseases. Microorganisms for denitrification are more difficult to cultivate compared to nitrifying microorganisms, such as Nitrosomonas or Nitrobacter. Denitrifying microorganisms are also called heterotrophic bacteria, and they require organic carbon as food as well as oxygen. Therefore, in wastewater treatment applications, a certain BOD amount has to be maintained in the anoxic basin. This is achieved by recirculating sludge from the secondary clarifier and aerobic basin back to the anoxic basin. The heterotrophic bacteria then try to oxidize the available BOD under the consumption of oxygen. However, as no dissolved oxygen is present in an anoxic basin, they have to look for alternative sources. Heterotropic bacteria has the ability to strip the oxygen from nitrate, NO3-, and to convert nitrate to nitrogen gas, N2. The nitrogen gas floats then as bubbles to the water surface and into the atmosphere. The activated sludge process usually separates the anoxic basin from the aerobic basin, either by building two different tanks or by creating different zones within one basin with controlled aeration or by on-off operation of aerators. It was found that under certain conditions, microanoxic zones can be formed inside bacteria layers. This effect, which is also known as simultaneous nitrification denitrification, NSDN, is especially benefited in submerged fixed bed reactors. Here, microorganisms are attached to a film media surface and form a biofilm layer. While the top layers of microorganisms consume the available oxygen to oxidize ammonia, deeper layers are forced to strip oxygen from nitrate, NO3-, to produce nitrogen gas, N2, within a fixed bed reactor. The SNDN process can also be combined with different aeration zones or on-off aeration for improved denitrification results. Thanks for watching, and if you like our 3-minute tutorials, please subscribe and don't forget to give a thumbs up.
Okay, our next video is on the phosphorus removal, because today we studied both, joint removal of nitrogen and phosphorus. So our next topic.
Wastewater, produced for engineers, system owners, management, and personnel to answer commonly asked questions about wastewater applications and Medora Corporation equipment. How can Medora's floating wastewater mixing equipment be used to meet phosphorus limits in a wastewater lagoon? In the next 3 minutes or so, we'll explain the basic process and equipment needed to achieve the best, most economical, and easiest phosphorus removal in the industry. Where to start? Let's dig into some quick phosphorus fundamentals. Phosphorus is an abundant, naturally occurring element essential to all life on Earth. Excessive phosphorus in waterways and water bodies can cause environmental complications such as dense plant, algae, and cyanobacteria growth known as eutrophication. By removing phosphorus during the wastewater treatment process, there are less potential downstream negative impacts. Less phosphorus release, less negative environmental impact. And as time moves on, phosphorus discharge limits for lagoons will only become more strict, increasing the urgency for a reliable and effective phosphorus removal strategy. So let's get our removal on. Phosphorus can be removed from a lagoon by applying a precipitating agent like aluminum sulfate or ferric chloride. Once precipitated, the phosphorus harmlessly falls out of the water column and into the sludge sediments. Precipitant dispersal is a very hands-on and costly process requiring extensive labor, time, infrastructure, and accessory resources. In short, it can be spendy. This is where Medora's floating wastewater mixing equipment can make phosphorus removal a whole lot easier and more cost-effective. And it all starts with a floating wastewater mixer. The mixer is anchored using a single shore-to-shore tethered cable, which is able to span most lagoon dimensions. Once tethered, an injection hose is run from shore to the machine, fastened along the tether cable, terminating just below the machine impeller. And just like that, Medora's floating wastewater mixer is now ready to receive and distribute the phosphorus precipitant of your choice. Consult with your chemical supplier for proper sizing of metering pumps, chemical storage, and dosing rates for your lagoon. Then, all is left is the final connection to the mixer injection hose, and you're ready to rock. The phosphorus precipitating agent is sent from the onshore metering system down the injection hose to the machine just below the impeller. Here, the precipitating agent is fully mixed into the entire direct flow of the floating wastewater mixer. And this is where great mixing takes center stage. The well-mixed precipitant is then distributed radially across the lagoon utilizing proven long-distance circulation technology. It creates an ideal interaction environment between your precipitating agent and the target phosphorus. In many cases, when compared to traditional application methods, only half as much precipitant is needed to achieve better phosphorus removal, or simply put, the better the mixing, the better the phosphorus precipitation. And Medora wastewater mixing is the best there is. Even better yet, Medora Corporation has effective mixing
Okay, yeah. So these are the technology that they use normally to remove the phosphorus in the lagoon. Yeah. So they use the same method that we have studied before, precipitation method, where we use ferric chloride as well as alum. Yeah, the one that you have calculated before for your assignment, yeah, as individual assignment. The same method, but for this system, especially in the lagoon, they use a special mixer, yeah, so that the precipitant, yeah, or the aluminium as well as the ferric chloride will be better mixed with the phosphorus which is to be removed.
Options no matter your lagoon size. 1 acre, 15 acres. More, less, in between, doesn't matter. Medora Corporation has you covered. Medora Floating Wastewater Lagoon Mixers. Make your phosphorus removal strategy a more successful phosphorus removal strategy. For more information how Medora Corporation's wastewater mixing
Okay. So let's see one example on how to remove before we go to the system which has been improved for the removal of phosphorus as well as nitrogen. Let's see one example. This is a very simple example for a phosphorus removal in a lake. So a lake with a surface area of 80 times 10 to the power of 6 meters squared is fed by a stream having an average flow of 15 meter cube per second and average total phosphorus concentration of 0.01 milligram per liter. Yeah. So in addition, treated effluent from a wastewater treatment plant adds 0.2 meter cube per second of flow having 5 milligram per liter of total phosphorus. Yeah. So this is more on the balance, yeah, on the mix, on the balance of the phosphorus flow into a lake. Yeah. So noted that the total phosphorus settling rate is equal to 10 meter per year. Okay. First, estimate the average total phosphorus concentration. Number two, determine the rate of phosphorus removal at wastewater treatment plant would be required to keep the concentration of phosphorus in the lake at an acceptable level, of 0.01 milligram per liter. Okay, now in this question, there are two steps, for you to answer. The first one, estimate the average total phosphorus concentration, and the second one, you are given the acceptable level, the allowable limit, of the phosphorus. Now you have to calculate, what is the phosphorus that can flow into the lake to maintain the allowable or the acceptable limit of the phosphorus, which is 0.01 milligram per liter. Okay, next. All right, first, average total of phosphorus concentration, P loading from the incoming stream. Yeah, if you can go back to our, question here. Okay, yeah. So this the surface area 80 times 10 to the power of 6. You are also given the flow, and the flow of a stream. This is the flow of the stream, yeah, and average total phosphorus concentration. These are the total phosphorus concentration from the lakes, yeah, which is available in the lake occupied by a stream. Oh, sorry, this is not, okay. Okay, these are the phosphorus which is available, yeah, which is available in a stream, yeah, in a stream, yeah, also from the stream. In addition, treated effluent from a wastewater treatment plant, okay, treated effluent from a wastewater treatment plant, yeah, with the flow, as well as the concentration of the phosphorus. This is both from wastewater treatment plant. You are also, on top of that, you are also given the settling rate of the phosphorus. The settling rate of the phosphorus, meaning to say that the phosphorus coming from the storm water, which is the non-point source. Now, the one that we have been discussing is the point source. First, the phosphorus from the stream, from or the river into the lake. Second, the phosphorus from a wastewater treatment plant. Yeah, these two sources, are considered the point source of phosphorus into the lake. Therefore, whenever we calculate for the phosphorus removal, we have in an open area like a lake, so that we have to consider the settling rate. So that so that will cover the phosphorus incoming flow of phosphorus from the stormwater, from the biological activities. So these are the value which is 10 meter per year. Okay, estimate the average total phosphorus concentration. So the loading, this is the phosphorus loading from the incoming stream. You are given the flow rate, you are given the concentration, so that this from the incoming stream, the phosphorus is equal to 0.15 gram per second. Phosphorus from the wastewater treatment plant. You are given the flow rate, you are given the concentration, so you can calculate the load, gram per second from the wastewater treatment plant. So comparing between these two values, the incoming phosphorus is higher from a wastewater treatment plant due to the higher concentration of phosphorus. If you compare between these two values. Next, total phosphorus loading equal to 0.15 plus 1. So from the point source, these are the point source, is equal to 1.15. Next, flow rate of the lake would be the sum of the inlet stream flow and the effluent flow. Okay. Okay. So this is to answer the average total phosphorus concentration. Okay. This is long step before we can reach this step. Step number 1, step number 2 until step number 6 are to answer question A. Because A asks you to estimate the average total phosphorus concentration. Okay. Now you have calculated the total loading of the phosphorus. Next, knowing the Q value, what is the Q value? These are the Q from the river or the stream, and these are the Q from the wastewater treatment plant. Okay, so these are the total Q. Then you can calculate velocity of the phosphorus in the lake. So the velocity is equal to the settling rate. The settling rate of the phosphorus over years, 24 hours. This is only the unit conversion. So this is to change the unit from meter per year to meter per second. Okay. Send me your WhatsApp message. Okay, not from you. Okay. I thought that any of you send me a message. All right. Okay. So now this is only to convert from meter per year to meter per second, which is the settling rate, phosphorus settling rate. Then average total P concentration equal to S3. What is S3 just now? S3 is the total loading of the incoming flow of the phosphorus over Q in over Q out plus Q in. So 1.15 over 15.2, which is the total Q. Where do I get total Q? From here. Where do I get this value? This value both are available in the question, which is the flow rate of the phosphorus, flow rate of the river, as well as the flow rate of the wastewater treatment plant, of the flow from wastewater treatment plant. So that Q out equal to 15.2 meter cube per second plus 3.17 times 10 to the power of times 10 to the power of minus 7, which is the settling rate. You are given the settling rate in meter per year. You are converting to meter per second. Then this is the area of the lake. Area of the lake. So that you will get the total phosphorus concentration is equal to 0.028 gram per meter cube or 0.028 milligram per liter. Okay. Next is to calculate the rate of the phosphorus removal at wastewater treatment plant would be required to keep the concentration of the phosphorus in the lake at an acceptable level. Now, if you are to compare between the flow if you are to compare between the concentration from the wastewater treatment plant as well as the from the river, you can see there are significant difference. The concentration, this is one from the river, this is one from the wastewater treatment plant. You can see the difference is significantly, this is significant difference. That's why we have to further monitor the concentration of the wastewater, because there are some restriction here. Restriction in the lake, because we know that phosphorus is the limiting factor. That can we have to control to avoid eutrophication. So that the allowable limit for the phosphorus here is equal to 0.01. So that the question asks you to determine the rate of phosphorus removal would be required. The rate of phosphorus removal at wastewater treatment plant would be required so that we can maintain the concentration of the phosphorus in the lake up to up to the maximum of 0.01. Okay, how to calculate this? To reach 0.01, total phosphorus loading must be S4 equal to PQ plus VA. So P is equal to the limit which has been set earlier. Which has been set earlier, 0.001. Which one? This one is the total. This one is the total Q. Okay, 3.17 is the phosphorus settling rate. Settling rate. This one is the area. Okay, so it's equal to 0.41 gram per 0.41 gram per second. Okay, therefore the maximum phosphorus can be released from wastewater treatment plant is 0.41 minus 0.15 here. 0.15, where do I get 0.15? From here. So this one, because we know that we have to consider this. You know why? Because 0.15 is the fixed value from the river. Let's say we have a fixed value from the river, so that we only have the fluctuation of the phosphorus in the incoming flow from the wastewater treatment plant. For that reason, we have to minus the value of the phosphorus from the river or the stream. So 0.41 minus 0.15. Where do I get this value? This value is the allowable limit. This value is the allowable limit which has been set in the question earlier. Next, next. Minus 0.41 minus 0.15 equal to 0.26. So since S2 is now equal to 1 gram per second, therefore 1 gram per second from where? From here. From here. So therefore, the existing concentration of P is 74% higher than the allowable limit. Okay, how do we know 75% higher? Because now we already have 1.0 gram per second, but the limit which is available is only 0.26. So that's why it's 75% higher. Okay, how do we calculate this? 1.0 minus 0.26 divided by 1.0. Okay, that is the limit that we this is how we can reach 74%. Okay. Stop presenting for a while. Okay, let me find another slide. Yes. Okay. Let me find another. I would like to share with you another example. Yeah, so give me 5 minutes to find the example. Mm. This one. I cannot find the example because it's belong to another course which is very related to this. It's belong to a master course. I was thinking that I can share with you, but never mind. Since I couldn't find the examples, this example, the one I shared with you just now, is sufficient. Yeah, maybe just try that. Maybe we can find another one. Okay. Okay, so these are the value. Yeah, these are the existing concentration of the phosphorus flow into the river, while this 0.26 is the maximum. Yeah, 0.26 is the maximum. That's why we have to remove 74%. So that's why the final sentence here, therefore the existing concentration of phosphorus is 74% higher than allowable limit. Yeah, because the allowable limit is they have set, yeah, we have used the allowable limit to 0.01, but since we have the system has been released into the lake is about 1 gram per second. Yeah, so that and we know that to achieve the allowable limit, let me get the green one. We know that the allowable limit is 0.01 milligram per liter. Okay, but the system has been released into the system into the lakes, from the wastewater treatment plant is about 1.0 gram per second. Yeah, in order to achieve the allowable limit, the system from wastewater treatment plant, the phosphorus in wastewater treatment plant should be released into the lakes, the maximum value is only 0.26. That's why it's require 74% of the removal. Yeah, because comparing between these two value is require 74% is actually high, 74% higher than the allowable limit. Yeah, so this is the facts, yeah, of the phosphorus flows into the river, into the lakes. But considering the settling rate, the evaporation rate, sometimes the settling rate as well as the allowable limit is not too stringent, because sometimes the phosphorus can also release into the air through evaporation process. Yeah, not really depends on the treatment, not really depends on the biological process, yeah, but physical process, yeah, also can release some of the phosphorus into the air. Okay, all right, so let's continue our next lecture. Is on joint phosphorus and removal, joint phosphorus and nitrogen removal. Okay, about joint phosphorus and nitrogen removal. Okay, these are biological methods. Right? The methods that I'm going to introduce to you are basically the method that we have studied before. But the difference is these are considered as a combination. They have actually redesigned or rearranged the flow of the anoxic process, of the aerobic process for the better removal of phosphorus and nitrogen. Yeah? Okay, let's see. Expose of alternate anaerobic and aerobic condition to microorganism, yeah, it will improve uptake of the phosphorus, will be above the normal level. Yeah, so that we know, yeah, we have to introduce the aerobic as well as anaerobic process. Yeah, because having these two processes, because each of these two steps have their own function. Anaerobic, for example, have the capability to oxidize or to treat, has the capability to treat or to respirate to break down the high concentration or high loading of the organic matters. Yeah? While the aerobic process has a good has the advantage, of further improving the quality of the treated wastewater. But for this reason, during these two processes, it will also produce the phosphorus. Yeah, it will also produce the phosphorus. Yeah, so phosphorus is also required, not only to utilize for the cell maintenance and energy transport, but it's also stored the subsequent use, by the microorganism. Okay. In each of the microbe cell, there are one pump, which is known ATP pump. Yeah, ATP pump is the pump, which is been working to pump in and out the cation and anion, so that the precipitation will occur within the cell of the microorganism. Phosphorus is one, of the substance which is required, to metabolize the cell of the microorganism. Okay, so we have actually four. We have aerobic process, a process with the oxygen. Oxygen is available. Anaerobic process is the biological process without oxygen, with the absence of the oxygen, and anoxic process with the nitrogen converted biological to nitrogen in the absence of oxygen. Again, if we can go back to our slide, our video just now, how do they define the anoxic process? It's a process where it's occurred in low concentration of the oxygen environment, which is less than 10%, and the oxygen, the source of the oxygen is from nitrate, NO3. The source of the oxygen is from nitrates. Okay, these are the processes. We have A to O process, A or O process, which is anaerobic, then oxic process. The mainstream is for phosphorus removal, a phosphoric process, which is the side stream phosphorus removal, as well as sequencing a batch reactor, the one that we have studied before. Yeah. So sequencing a batch reactor have I mean uh, the innovation, yeah, of the sequencing batch reactor has improved a lot. Yeah? The removal of phosphorus and nitrogen, because started from this innovation, they have actually improve SBR to become another system for further removal of nitrogen as well as phosphorus. Okay, these are the combined carbon oxidation and P removal. Yeah, this is A to O process. A is aerobic, O is the oxygen process. Yeah, so and sorry, A is the anaerobic, O is the aerobic stages. Yeah, so these are the common, yeah, the common technology that we use anywhere. Yeah, anywhere that they introduce a combined process of anaerobic as well as aerobic, they will introduce aerobic first. Yeah, aerobic will be introduced first. Why aerobic has to be introduced first? Because they have the capability to they have the capability, aerobic system has the capability to treat higher organic loading rate, yeah, as compared to aerobic. Aerobic also can, yeah, but the problem with the aerobic is if you would like to treat a higher concentration of waste using aerobic system, then you have to supply more oxygen. Yeah, you have to supply more oxygen. That's why we introduce anaerobic first, so that after the treated waste from the anaerobic will flow into aerobic, it will further improve the quality. And also, you don't have to supply too high concentration of the oxygen. Okay, so it's a combined carbon oxidation and phosphorus removal, a single stage suspended growth system. Yeah, so that's why I said just now, this is the improved version of the sequencing a batch reactor. Sequencing a batch reactor is a suspended growth system where the sludge is available in the tank. Okay, it's a combined anaerobic and aerobic section in a sequence. So normally the BOD to phosphorus ratio is about 10 to 1 lah. Yeah, 10 to 1. So it's good. Yeah, if this is the recommended ratio whenever you are employing this system, so that if we have the BOD, yeah, BOD has to be 10 times higher than the phosphorus level, so that the system works well. Okay, next. Okay, these are the sequencing batch reactor for the removal of phosphorus and BOD, periodically operated field and raw activated sludge process, the one that we have studied before. Phosphorus release and BOD uptake occurs in the anaerobic state, yeah, with a subsequent phosphorus uptake in the aerobic state. Yeah, so overall cycle about 3 to 24 hours. Yeah. So an anoxic stir may be inserted between aerobic and settling reactor. So we have 4 main steps in the SBR process. If you still remember, we have a filling process, decanting process, settling process, aeration process, and also decanting process. These are the 4 main stages of the SBR. Okay, let's see. This is what we would like to focus today. The SBR is the original version, yeah, of all these processes. Yeah, it has been designed for the removal of phosphorus as well as the nitrogen. Nevertheless, today we will see the improved version. Okay, we would like to see the improved version, yeah, of the SBR, so that we can remove both phosphorus as well as nitrogen. So the first one is A2O2 process, yeah, where we have anaerobic as well as aerobic process, but we have to the power of 2. The second one is known as 5-stage but then 4 process. The third one is a UCT process, and the fourth one is VIP process. Okay. Okay. Okay, let's see one by one. And you have to be careful, yeah, with the difference between each of the process, because, yeah, why? Um, they looks like the same, but they are not the same. Yeah, they looks like the same, but they are not the same. Why? Because how do they arrange the system is the change where the point to recycle the sludge, they change the arrangement of the each phases. Yeah? So this is where that you need to pay attention. Okay, first let's look one by one. Yeah, first A to O process. Yeah, similar to the previous the common SB as well as oxygen process, but at anoxic zone for the denitrification process. Yeah, so we have watched the previous video has explained to us. What is the significance of denitrification process during anoxic zone? First, denitrification process only occurs during anoxic zone. Only occurs in anoxic zone because these are the zone with oxygen less than 10%. Am I right? Yeah. So, yeah, this A to the power of 2O process, yeah, the only difference is they have anoxic between the aerobic as well as anaerobic process. Yeah, why do we have this? Because they would like to promote the denitrification to occurs. Yeah, because denitrification only occurs in anoxic environment. Okay, it won't occurs in anaerobic environment. It will only occur in anoxic environment because it still requires small percent of the oxygen. Yeah, in this case, you can see, yeah, the one in dotted line, yeah, is the sludge. The one in a full line is the recycled effluent. In this stage, you see after the aerobic process, yeah, the influent, yeah, sorry, recycled influent, yeah. So the influent will be going back to the anoxic stage. Why do the influent after the aerobic stages? Yeah, you can see here. Can I get okay, you can see here, yeah, from the after the effluent, yeah, the treated effluent from aerobic stages, it will go back to anoxic stages. Yeah. The reason why that they have to do this because they would like to promote the denitrification process. Yeah. Why? If during denitrification process, some BOD is required. Yeah. If you go back to the equation of denitrification process, is a BOD, yeah, BOD plus microbes. Yeah, so that's why I said, yeah, we have, in order to promote more denitrification process, then we have to recycle the effluent. Yeah, sorry, we have to recycle the influent. So that why we have to recycle the influent? Because in the influent the BOD is available. Yeah, in other words, microbes require food. Yeah, because BOD is the food for microorganism, kan? So the food which is available after aerobic process will be recycled again into the anaerobic stage, so that we can promote more denitrification process, and the detention time is only 1 hour. Yeah, so these are the difference between A2O process and also the A without AO process. Yeah, AO process is the common SBR lah. Yeah, is the common SBR. While in this one, they have another tank which is known as anoxic tank, and the retention time is 1 hour. And you need to know what the reason why they have to recycle the effluent from aerobic stages. Yeah. Okay, next, yeah, is known as 5-stage but then 4 process. Yeah. So what is the difference between this one and the previous one? First, we have anaerobic process, the same. Okay. Next, we have anoxic process, the same. And we have aerobic process and anoxic process and aerobic process again. Yeah. You see, in this stage, yeah, they have introduced 2 steps of the anoxic. Yeah, they have introduced 2 steps of the anoxic, yeah, which is first one and the second one anoxic, and they have 2 steps, yeah, of the of the aerobic. Okay, so these are the different. The first difference is how they do configure, how do they introduce the extra stages, yeah, for the anoxic as well as aerobic. The second difference is how they recycle the influent. The influent after aerobic are being recycled again into the anoxic zone. Again, to promote to have more food, yeah, for denitrification process. Yeah, it's being recycled after the first stage of the aerobic process into the anoxic zone. Okay, and the rest I think the same. The sludge recycle from the clarifier to the influent. Yes, the sludge movement is still the same. But you have to know the difference because sometimes in the question, uh, not only the difference in terms of the configuration, yeah, but also the difference in terms of the process, the significance of why do we need to arrange another set of anoxic, why we need to arrange another set of aerobic, what is the significance of having this. So that you need to know the function of anoxic. Anoxic is to promote more denitrification process, to further removal of the nitrogen, turns the ammonium into nitrogen gas, while aerobic process is for further removal of the carbon, yeah, for the further removal of the BOD. Okay, anaerobic, anoxic, and aerobic stages for P and C removal, yeah, phosphorus, nitrogen, and carbon. Second, anoxic stage for additional nitrification. Last aerobic stage is to use to strip residual nitrogen gas. Okay, so this one is to strip residual nitrogen gas after and to gas after anoxic process. So the first aerobic process is for the removal of carbon. This one is for nitrogen. Yeah, this one is for carbon. So this one again for nitrogen. Yeah, this one again. This one is for N2. Yeah. So that you need to know the function of each of these. Okay. Next step is the UCT process. Yeah. So first UCT process we do have anaerobic. Yeah. We do have the anoxic. Yeah. The same. And we have another anoxic tank and aerobic tank. So in this case, yeah, the difference is we have two steps of the recycling of the effluent. The first recycled effluent is from anoxic to anaerobic, yeah, and the second second stage for the recycled effluent is from aerobic to the anoxic. Okay, the first function, yeah, of the aerobic to anoxic, of course, definitely to add food so that they can promote the denitrification process. But in this case, yeah, food after anoxic stage, it will recycle back into the anaerobic because in this they would like to reduce the carbon content. Yeah, to reduce the carbon content, then flow again into anoxic and another anoxic environment. But we believe that, yeah, uh, most probably in this anoxic environment, the food might not be sufficient enough, yeah, because they have already employed the first recycling process. Yeah? That's why they have to employ another set of recycling process after the aerobic tank. Yeah. So in this case, the sludge, yeah, also different. Yeah. If you notice, yeah, the sludge in the previous 5-stage Bedenfo process as well as the A2O process, the sludge being recycled into the influent. While in this case, yeah, the sludge are not being recycled into the influent, but are being recycled into the anoxic tank. Yeah, similar to A2O process. However, return activated sludge is recycled to the anoxic stage instead of aeration stage, and the internal cycle is from anoxic stage to anaerobic stage. Yeah, so why? Yeah, why the sludge are being recycled into anoxic environment instead of the first stage of the process? Yeah, so in this case, yeah, they would like to improve first. They would, since we have already one recycling process, so that we can further improve the carbon content, but having sludge, yeah, flowing into the anoxic, yeah, will improve the mixed liquid suspended solid in the anoxic. tanks. Mixed liquid suspended solid. Okay. The last step is known as VIP process. VIP process, first we have anaerobic stages, we have anoxic stages, same, then aerobic stages. They are exactly the same as A2O, but the difference is they have two recycling process. The first process is anoxic, flow into the influent tank, and the second recycling process after the aerobic flow into the anoxic. Okay, first, the reason why that anoxic flow into will go back to the influent is to further improve the quality. Further improve the quality of the carbon concentration, and again after the aerobic process it will flow into anoxic environment to promote denitrification for food supply. And again in this process, if you notice, the sludge return into anoxic stages. So it looks like in this process, VIP is the process where they don't use so many tanks, but they uh, they focus on one tank which should be able to promote denitrification process. Okay, so I think that's all. These are the processes that involve for the joint carbon, for the joint nitrogen and phosphorus removal, but not to be forgotten. We are focusing on the phosphorus and nitrogen removal, but all of these processes, they should be able to remove the BOD, to remove the carbon. But sometimes in many treatment process, carbon is not a problem. It can always be removed. But when we go to certain types of the pollutants, certain types of substance, then that's why we need to do some modification, some rearrangement for further removal of this substance, because it requires special process. For example, like nitrogen and phosphorus. Okay. Before we end our lecture today, I would like to discuss with you about the project. Because I have uploaded the project last week, but I think we haven't yet discussed. Let me find the question for the project. I have uploaded. Okay. Okay, these are the project. A wastewater treatment plant is to be designed for a newly developed area. Located within the vicinity of a forest reserve park. Okay. Given that the current population is 1,000, since this is a newly developed area, the current population is only 1,000, you are to design a wastewater treatment plant for only biological process unit of RPC, which can serve the purpose of BOD removal. You are to submit a design report containing first growth area and the population trend for a design period of 15 years. You are to design for a 15 years period. Okay, in my notes I have included the calculation on how to estimate the population. You are not restricted to only the methods which I have used. I think I have been using the arithmetic methods, but you can use other methods. You can Google other methods which can be used to estimate the population. There are geometric method. There are a few other methods that can be used to estimate the population. Sorry. So that you can use that methods, because the current population is 1,000. You have to estimate the population after 15 years. Okay, next, number 2, environmental and community concern in the service area for the project planning. Okay, propose 4 possible activities and other following aspects that should be addressed in the environmental impact assessment. I hope you are familiar with this. We have studied before environmental impact assessment report during the construction phase of this project. Okay, so identify the residual impact for any of the activities. Okay, if you have One second. Okay, all right. These are the summary. These are the summary. I believe that we have seen this before. So, summary of a project related environmental consequences. So these are the summary. For example, the activities that occurs during the preparation stage. But you don't have to worry. You only sorry. You only need to address about 4 activities only, but during construction phase. Let me share with you the example. Okay, for example, this one. During construction phase, please do not copy and paste from this activity because this is different project. This is the environmental impact assessment report which has been prepared for the university project. But you are to prepare, you are to address the issue for a construction of a wastewater treatment plant located within the vicinity of the forest reserve park. Okay, so for example, the activities during construction phase of a university is the earthwork. So the impact is the loss of the soil particle. That will be the impact. So what is the significant environmental impact? Significant environmental impact, so will be the loss of topsoil. What is the proposed mitigation measures? The proposed mitigation measures can be the staging. We can provide the detention pond, and there is no residual impact. Okay, but in your case, since you are proposing a project within the vicinity of a forest reserve park, so you have to be careful. Propose mitigation measures, and actually I will alter this. I will re-uploaded this question because actually you have to address any residual impact. Residual impact. Oh, never mind, you can write the residual impact at the bottom of this table letter. Residual impact means to say that the impact which is cannot be mitigated. In other words, the damage is permanent. For example, there is no way of solving the problem. If you would like to proceed with the development, then definitely there will be some bad negative impact to the environment. For example, marine environment, the effect, the effect of the to the fishermen, for example, that will be permanent. If we would like to develop a port, for example, near a coastal area, so that is considered as a permanent impact. So that can be classified as residual impact. So for this project, you have to identify. Okay, so identify the residual impact for any of the activities that you have addressed. Number 3, land area required. So land area required, this is based on the loading, so that you can refer to my example which we have studied in week 6 on how to calculate the area based on the loading. Very straightforward. And number 4, this is the one that we studied last week. on the design of a RBC for BOD removal if projected population. Yeah, okay. Question number 4. You are you are to use the population of 12,000. Even though here you have estimated the population, let's say you got 25,000, yeah, but do not use your value, use this value of 12,000. Yeah, so given the following information, yeah, the BOD consideration, the solid BOD, then remember you have to calculate to design for peak flow condition. So remember to use the equation of 4.7 p to the minus p to the power of minus 0.11. Yeah, so then only you can get the flow rate. The flow rate is not given here. Yeah, the flow rate you can obtain from the numbers of population, but you have to consider the peak flow factor, and the rest is just the step exactly the example. So most of them are straightforward, except you have to calculate for peak flow condition. And then number 2, yeah, number 1 straightforward, number 3 very easy, number 4 you have to get the numbers of population correct. Yeah, if you got it right, then you will be getting the right answer for the rest of the question. Okay, propose the numbers of stages and train required in a peak flow condition to achieve target effluent less than 10 milligram per liter of soluble BOD. You are given the area per shaft is 18,000 meter square per shaft. These are the manufacturers design for the area per shaft. In our example, we use 9,300. Okay, so I think that's all. Yeah, I'm not going to re-upload the question because you can simply address the residual impact, the residual impact for any of the activities, related activities, but it's required. Yeah, it's 16 months. Yeah, so please address the activities as well as the necessary mitigation measures, significance to environment, as well as the residual impact. Okay, so I think that's all. Any question regarding on the project? Okay, the project, the submission is 5 days after the final exam. Okay, the submission for the project is 5 days after the final exam. I think I have uploaded in Putra Blast, and the deadline I put as 31st of July, but I will I will again amend the date of the submission once we have confirmed the date of the final exam. 5 days after the final exam, meaning to say that final exam for this course, which is ECV 4412, not for overall courses. So once we have got the date, I will amend the date for the submission, which is 5 days after the final exam. And please let me know in case that you have any question regarding on the project. This is ongoing basis. It's a long-term assessment. So that's why you are given sufficient time. You have at least 2 months to complete this project. It's a long-term assessment. So please do this well and take your time. Take your time. Okay, so I think that's all for today. You have any question?
I think no, Doctor.
Okay. Thank you very much, Dinesh, for sharing the slide, and no question. Thank you, everyone. So I'll see you again next week. Okay, bye.
Thank you, Doctor.
All right, thank you, Doctor.
Okay, thank you. Bye. So,
Thank